In our third example, we'll take a look at a multiple charge arrangement. So I have more than just two charges. I've got a 12 microcoulomb charge located 9 centimeters to the left of a negative 3 microcoulomb charge, and a negative 9 microcoulomb charge located 15 centimeters to the right of even that. What I'm asked to find is the net force on all three of these charges. So it's a little bit trickier here because A is not just being affected by B, C is also exerting some kind of force. Same thing, B is being affected by both A and C, so we have to kind of take all of this into account. This is a fairly time-consuming problem, so you won't expect to see a ton of these, but you should know how to solve it, so I want to solve one out for you so you understand the process. And this is a comprehensive problem, so we'll use that whole problem-solving list that we led off with in the other video. So one slight adjustment here, but let's go ahead with the problem-solving method as we've stated it previously. The first thing we should always do is list our variables. So we'll start with that. The K value is always 8.99 times 10 to the ninth. Charge A is 12 microcoulombs, which is 12 times 10 to the negative sixth. Charge B is 3 microcoulombs, 3 times 10 to the negative sixth. And charge C is negative 9 microcoulombs, or negative 9 times 10 to the negative sixth. I'll convert what I'm calling R1, 9 centimeters is 0.09 meters, and R2, 15 centimeters is 0.15 meters. Now, the next step, which I heavily recommend, would be to draw those arrows. Now, it becomes a little bit more important. So, I say to myself, A and B are both positive, so that means B is going to repel A. So that means the force of B acting on A will push A to the left, because B will repel A. But A is positive and C is negative. So despite being pretty far away, there's still some kind of force between A and C. And since that's an attractive force, the force of C on A will be attractive. It'll be attempting to pull A towards it. All right, for B, B is going to be repelled by A because they're both positive. So that's going to point to the right, the force of A on B. C is negative, B is positive. So the force of C on B is actually going to be going to the right as well. So despite there being one repulsive force and one attractive force on B, based on the geometry, they're both going to be acting to the right. And if we do the same for C, well, C is negative, the other two are positive, so both of those will be attractive forces. So you can see here that A is going to attract C to the left, B is going to attract C to the left. And now we have a general idea of what's going on. That's going to help us down the road when we decide whether to add or subtract these forces that we're going to calculate in a second. All right, so to first figure out the force between A and B, well, we have to do Coulomb's law a few times here because Coulomb's law only has two charges in it and we have three charges. So we have to do Coulomb's law actually three times, once between A and B, once between B and C, and then once between A and C. So let's start with between A and B. So what we know is that the force of A acting on B and the force of B acting on A, those are going to be equal. Newton's third law states that if A acts on B, then B acts on A with an equal and opposite force. So those forces, A on B and B on A, they'll be equal. They'll just act in opposite directions, as you can see in our diagram. The force of B on A acts left, and the force of A on B acts right. So that's Newton's third law in action right there. So anyway, K value in, the charges in, 12 and 3 times 10 to the negative 6 respectively, and charges A and B are 9 centimeters or 0.09 meters apart. So I'm going to square that. I'm going to plug all that into my calculator, and you should get 39.96. It's a positive value. So I would suggest you get in the habit of writing the word attractive or repulsive instead of a positive or negative. So this is a repulsive 39.96 Newton force between A and B. And that's step number one, but I still need to figure out between B and C and between A and C. So if I want to do A and C next, it doesn't really matter what order. Well, the force of A acting on C has to be equal, but in the opposite direction of C acting on A. And again, in our diagram, that's true. A on C goes left, and C on A goes right. I'm going to do the same thing. Plug in K, plug in my 12 microcoulombs for A, but now my negative 9 microcoulombs because this is C. And I don't want to plug in 0.9 or 0.15. I want to plug in 0.24 because the 9 centimeters plus the 15 centimeters, that is how far A is from C. So I'm going to divide that by 0.24. I have to add those two together. I get 16.86 newtons when I plug this in my calculator, but I actually get negative because one of those charges is negative and one is positive. You will not see me write the negative. You will see me write the word attractive because that's what the negative suggests. If you leave the negative, you might get yourself tripped up when you go to plug these values in the final step of this problem. So I can't recommend enough. Don't write a positive or a negative. write repulsive or attractive. You will save yourself a lot of heartache. All right, we'll do the same for between B and C. So B and C and C on B equal and opposite forces. Okay, plug in those charges. In this case, B and C are separated by 15 centimeters or 0.15 meters. If you plug that in, you should get 10.79. Again, you get a negative value. I don't write the negative. I write attractive. I let the arrows up top tell me whether I'm going to add or subtract a force. Okay, so now, again, a little tedious, a little time consuming, but now that I have all of these forces, here's how I use this information to determine what the net force is on A, on B, and on C. So I'm going to assume for now that right is positive and left is negative, as we've done throughout the course. So looking at that, if I look at A, if I look at the charge A up top, I have the force of C acting on A going to the right, so I'll make that positive. That's why FC on A is positive. FB on A is actually going to the left, so I'm going to make it negative. I'm going to subtract it. So what I'm really doing here is taking the force of C on A, which is to the right, and subtracting the force of B on A, which is left. And now I just go up and I kind of find my values from all those calculations that I did above. So what this really means is the 16.86, that's C on A, so 16.86 to the right, minus, well, B acting on A is 39.96. So I'm going to subtract that value, and I get negative 23.1. And in this case, we're not using Coulomb's law. So Coulomb's law is where negative means attractive. In this case, I'm literally just summing forces. So, well, I assumed left was negative, so that tells me the net force on A is negative 23.1 newtons, or 23.1 newtons to the left. Why am I now assuming that left is negative, whereas before I assumed it was attractive? Because before I was using Coulomb's law. Here I'm simply summing forces, and I've defined right as positive and left as negative. I know that can be a bit tricky. Just make a note, you only need to worry about that when you're using Coulomb's law. I didn't use Coulomb's law. I'm just simply summing forces here. All right, if I look at B, if I look up at B, I notice that FAB goes to the right. FCB goes to the right. Well, that means they should both be positive because they're both going to the right. And in fact, that's what happens. I take the force of A on B, and I just simply add to it the force of C on B. Before I subtracted, because they were going in opposite directions on A. For B, they're both going in the same direction, so I simply add them together, and I just go up and I find A of B, which is 39.96. I find C on B, which is 10.79, and then I just add those two together. So I wind up getting 50.75. That is a positive value. This is not Coulomb's law, so the positive value tells me right. So that means the net force on B is 50.75 newtons acting to the right. To find C, I'm going to do the same thing, but I'm going to notice they're both going to the left, F of A on C and F of B on C, so I should just make them both negative. So I'm going to take negative FAC, and I'm going to add to that, or subtract. I'm going to add a negative FBC, or just subtract FBC. They're both negative, and if I plug that in, I wind up taking negative 16.86 minus 10.79. Again, they're both negative. They're being added together in the negative direction. I get negative 27.65. which tells me 27.65 newtons in the leftward direction. Very time-consuming process. Expect when you see this, you may only be asked to find the net charge, the net force on like one of the charges. You're rarely going to be asked to find all three of them unless it's like a practice worksheet just to get the method down. So you won't have to do all of this, but please make sure you understand this process. You will have to look at multiple charges, and you need to understand how drawing the arrows, calculating using Coulomb's law multiple times, and then determining whether to add or subtract those forces is probably the simplest way to solve something as comprehensive as this.